n is not equal to 0 is called a rational number. For example, we can in fact give any example, but I want to give the ones that is given in the text. 1 by 3 minus 4 by 9, say 200 by 13 and 57. Note that this is an integer, but it's also at the same time a rational number, because we can express 57 in that form as a quotient of two integers. One of them is 57 and the other is 1, and where the denominator of course is non-zero. So all these are examples of rational numbers. Now rational numbers themselves come in two different categories, and they are like this, depending on the decimal type of decimal expansion that they have. The rational numbers are precisely those real numbers whose decimal expansions are, the definition involves this, that if a real number can be written in this form, then it's called a rational number. But what about in terms of decimal expansion, can we say something about which numbers are rational just looking at their decimal expansion? And it turns out that we can. Their decimal expansion should either be terminating or repeating, that are either a terminating, which means ending in an infinite string of zeros, for example 3 by 4, its decimal expansion is this. It's ending in an infinite string of zeros, which also is written like this, or either it is terminating or it is repeating. Or repeating, where a block of digits repeats over and over. or example, you can divide by 7 or by 11. Here they have provided an example where division by 11 has been done. Turns out to be like this. 2.09 bar. We often indicate the block of repeating digits by putting a bar over that block. The bar indicates the block of repeating digit. It turns out that if a number is a rational number in this sense, then its decimal expansion either ends in an infinite string of zeros or a block of digits repeats itself again and again without any end after the decimal point. Note that this repeating block it's not necessary that it has to start right after the decimal point. It may happen, I cannot provide an example at this point, but it may happen that say you have some digits before the decimal point, then you have the decimal point, then after that you have some digits, and then you get a repeating block. It's certainly possible. Okay, you may have come across such a situation, but after the decimal point immediately the repeating block does not appear. It appears after some digits. Okay, now now this that completeness, something about that completeness and the distinction between rational numbers and real numbers. The set of rational numbers has the same algebraic and order properties as the set of real numbers. That means if instead of considering the real numbers in general, if you restrict your attention on the rational numbers only, then they also have the same algebraic properties. You can add, subtract, multiply and divide two rational numbers to get more rational number which obey the same rules of algebra as the real numbers do. And also in the list of those order properties that we have shown, there that A, B and C you can consider rational numbers there also. They continue to be the same. So these algebraic and order properties fail to distinguish between rational and real numbers. However, the last completeness property does so. However, the system of rational numbers is not complete. For example, there is no rational number whose square is 2. In that sense, there is a gap in the rational line instead of calling real line, I am calling rational line. Namely, I am in the straight line, I am only considering those points that correspond to rational numbers. If I look at the set of those points on the real line, then there will be gaps. For example, the point where root 2 should be, square root of 2, will not be present in the set of rational numbers or on the rational line. So that's why it is not complete. There is a hole. There is a hole in the rational line where square root of 2 should be. So this is the primary reason for having the system of real numbers, and it is needed actually. We cannot do calculus with only the rational numbers. And examples of real numbers that are not rational, you already know. Real numbers that are not rational are called irrational numbers. And here are some examples. Oh, by the way, the fact that we are saying that the decimal expansion of any rational number should either be terminating or repeating also says that the decimal expansion of an irrational number is neither terminating nor repeating. It will, if you expand an irrational number such as root 2 in decimal system, then the digits will not end in a string of zeros, and neither will you find a block of digits which repeats again and again. These two things do not happen in the expansion of an irrational number, in the decimal expansion. So we can write they are characterized by having non-terminating and non-repeating decimal expansions. Examples of irrational numbers are, these are some easy examples: square root of 2 pi, say cube root of 5, log 3 to the base 10. Some such numbers are there which are not rational numbers. Many examples are of course there. There are infinitely many I said rational numbers, no? So these are irrational numbers examples of. Just like there are infinitely many rational numbers, there are infinitely many irrational numbers also. Okay, so now having seen these things, we are now going to look at, so these are arising because of the three very important subsets of the real numbers set we have identified, namely the set of natural numbers, the set of integers, and the set of rational numbers. But there are other subsets also, and they have names. Collectively they are called intervals. So next we look at intervals. A subset of R is called an interval if it contains at least two numbers and it contains every real number. The definition may look somewhat complicated at first, but we will decipher it. We will try to understand what it means. A subset of R is called an interval if it contains at least two numbers and it contains every real number lying between any two of its elements. Okay, it should not only contain two numbers, but if we choose arbitrarily any two numbers from the set, then all the real numbers lying between those two chosen numbers should also be there in the set. Such a set is known as an interval. For example, the set of all real numbers x such that x is greater than 6 is an interval, and so is the set of all real numbers x such that x lies between say 2 and 5 inclusive. So what we are saying here is that the set of all real numbers greater than 6 is an interval. Clearly this set contains at least two numbers, for example 7 and 8, and if you take any two numbers in this set that are greater than 6, then all the numbers lying in between these two numbers are also greater than 6. That means they also belong to the set. So this is an example of an interval. Another example is this: the set of all real numbers lying between 2 and 5 including 2 and 5. Clearly this set has at least two elements, 2 and 5 are there. Also, for example, 3 and 4 are there. And if you choose any two points in this set, then all the real numbers lying between those 2 points are also in the set. Because if you take these 2 points now, and if you take anything here, then since this point is less than this point and 2 is less than this, so automatically 2 will be less than this point. Similarly, since this is less than 5 and this is less than this point, so this point will be less than 5, so this point will be greater than 2 and less than 5, so it will belong to the set. I am just very roughly and in a very vague manner saying why these sets are intervals. However, let us now look at a non-example, that means a subset of R that is not an interval. However, the set of all non-zero real numbers is not an interval. If we consider the subset where we have all real numbers except 0, then that will not be an interval. The set, although this set contains 2 points, at least 2 points, for example, any 2 non-zero real numbers are there, okay, so but it fails the second condition. The set does not contain all the real numbers between -1 and 1. Note that -1 and 1 both belong to the set because both are non-zero real numbers, but all the real numbers lying between -1 and 1 are not there in the set. One number is not there, that is 0 itself does not contain, because 0 is absent from the set. Okay, so that is not an example of an interval. Now, this is an arithmetic definition. What does this definition tell us geometrically? Geometrically, intervals correspond to line segments and rays line segment and rays on the real line. Along with the real line itself. Okay, and there are some other things also that need to be said. Intervals of numbers corresponding to line segments are called finite intervals. intervals of numbers corresponding to rays and the real line itself are called infinite intervals. Okay, let us take some examples to better understand this thing. Say you have the real line like this, okay, where you have 0. Now because I am drawing without the aid of a ruler, it will look very bad, okay, but bear with me. So this is the real line. So let us take these examples themselves. X greater than 6, say we have 6 here. The set x greater than 6 geometrically denotes a ray, okay, which looks like an arrow, an infinitely long arrow whose one end is bounded and the other end has no bound. It goes on and on. That's why it's called a ray, much like a light ray, a ray of light. So all the real numbers greater than 6, they form a ray because they look like this, and this is an interval. It's called an infinite interval because it is a ray. As opposed to this, if you look at the set of all real numbers lying between 2 and 5, including 2 and 5, then geometrically that set corresponds to this line segment. So intervals corresponding to line segments are called finite in this sense, and rays are infinite. Note one more thing, that when we will draw such sets on the real line, the fact that the point 6 itself is not a part of the first set, 6 itself is not greater than 6, is denoted by drawing a hollow circle, okay, or a white circle. It denotes the fact that we have to take all the real numbers that lie on the right hand side of the point that represents 6. We cannot take 6 itself. Here, however, because 2 and 5 both are parts of the set, so we denote that fact by drawing black circles, completely filled out circle. If instead of this set, if we consider this set, for example, then the figure will look like this. Okay, it's a practice that is adopted to make sure which points lie in the set and which points do not lie in the set. You can call these points boundary points because they appear in the boundary of the set. We will properly define that also. Note one more thing, that the set of real numbers itself is also considered as an interval because it contains 2 points. In fact, it contains everything we are discussing right now, and it also contains every real number lying between these 2 points. So by definition it's an interval. However, it is one of a kind. It has all the real numbers and it's a ray that is in both directions. All the other rays are in only one direction, either on the right hand side or towards the left hand side. This, however, has both the directions, and it's also it's not called a ray, it's just simply called the real line itself. So now you understand what finite and infinite intervals mean and what line segments and rays have to do with intervals. Now some more terminology. A finite interval is called closed if it contains both its endpoints. Endpoints means points which appear in the boundary. If both of them belong to the set, belong to the interval, then we call such an interval a closed interval. Open if it contains none of the endpoints. And half open if it contains one endpoint but not the other. Okay, so if we are considering the set of all real numbers, say, that lie between 2 and 5 in this manner, then this interval is a closed interval. It contains both of its endpoints 2 and 5. This interval, on the other hand, contains neither 2 nor 5. So, by our terminology, it's called an open interval. The boundary points, none of them belongs to the set, belongs to the interval. The other two possibilities give us half open intervals. This interval, for example, contains 2 but it does not contain 5, so it is half open. It contains exactly one endpoint and not the other. Just like that, this interval contains 5 but not 2, so that is also a half open interval. And keep in mind these terms closed, open, half open, these have been defined only for finite intervals for us. Okay, they are not applicable to rays, or we are not calling rays open, closed or half open for now at least. The endpoints are also called boundary points. Together, they make up the interval's boundary. The 2 points together, if you consider them together as a set, then that set is known as the interval's boundary. The points in a finite interval that are not the boundary points are called interior points because they are inside. Together they make up what is known as the interval's interior. So for example, if we look at the set of all real numbers such that this, then 2 and 5 are boundary points and the set consisting of them is called the interval's boundary. However, any point lying between 2 and 5 which is neither 2 nor 5, for example 3 or 4 or say 3.615, in fact pi also belongs to this set because pi is greater than 2, less than 5. All these points are interior points. Any point in the interval other than the boundary points is known as an interior point, and together they